Hello everybody, and welcome back to part 3 of our ICRC Fungible token series. I know I had promised that we would be building a dApp to mint our ICDV token, but I haven't gotten to that yet, and I didn't want another week to go by without a video. So what I'm going to do today is go through what I would call what is ICRC1. So we'll go through not only the standard and what it gives us, but we'll also go through the ICRC1 package that we're using in the ICDV token, and I'll show you some of the features that we're not taking advantage of yet, but that we will eventually take advantage of. So first of all, I want to thank a number of people who minted ICDV tokens. I believe we've had almost 30 or 40, maybe more, ICP that's been used to mint ICDV tokens. Really appreciate it. That ICP goes directly to the ICDevs treasury, which is a 501c3, and that money gets spent on educational and scientific discovery around the internet computer ecosystem. And we try to help bring new developers in, we try to provide resources, and we're able to do videos like this. So if you want to go back to part 2 and figure out how to mint without a dApp, we'd love for you to do that. If you want to wait for the dApp, that's cool too. So let's go ahead and dive in here, and we'll start with what is ICRC1. So what is ICRC1? ICRC means Internet Computer Request for Comment. And you're able to file one of these ICRCs in a directory or in a Git repo. You're able to get an ICRC number by going to the repo github.com/definity/ICRC, going to issues and creating a new issue. Here you can see that we have a number of ICRCs that are open and working. So far, the only ICRCs that have passed through the NNS are ICRC1, 2, and 3. But we obviously have a large pipeline of these set up, and we're working through them all in working groups. If you want to join a working group, that would be amazing. We need people. We're trying to find ways to incentivize that work, but in the meantime, we need volunteers who just want to make the internet computer a better place. So ICRC1 was the first ICRC, and it's around fungible tokens. And I'm just going to go through this document. This is the final document that was ratified by the NNS about what ICRC1 is. And if you follow ICRC1, you should be compatible with most wallets that come out for the internet computer ecosystem that support ICRC1. So first of all, we're going to go through all these different objects. There's an account object. And an account is made up of an owner principal. This is like your public key. Then also a sub-account. Now there's a little bit of history here and actually controversy. Why do we have principals and sub-accounts? In Ethereum, everybody just has a public key. In Ethereum, your contract has a public key. And if Ethereum gets sent there, it all goes into one account for the contract, and the contract holds it. That's not a great pattern. It doesn't have what we call separation of concerns. So the issue with the internet computer is that we have canisters that also have public principals, public keys, and we don't want to hold everybody's funds in one account. And you see this firstly with the governance canister. If you have staked ICP and you've gotten very deep down that rabbit hole, you know that your neuron has its own account on the governance canister. And if you send ICP to that account, it will be added to the balance of your neuron, and every neuron gets its own account. So because we don't have derived principals for canisters, this is a feature that we would love to have, and it is actually key to a number of things that I want to build, and it's in the internet computer specification to do derived IDs, but canisters can't do them yet. So in the meantime, we had to have a way for canisters to hold funds in different accounts. And so the sub-account emerged. Now this led to some controversy because admittedly it's not the most obvious pattern because most of our users are Ethereum users. Now, If you step back from crypto and you say, hey, I have a bank account and I would love to have a budget and I would love to have a way inside my bank account to have sub-accounts. So I could put my mortgage money in my mortgage account. I could put my car money in my car account. I could put my food money in my food account. This is a much easier way to think about why we have sub-accounts. We want to give every user a way to apportion their funds into their proper buckets. So a sub-account is like a bucket. When we send funds, we send them to an account which is a mixture of a principal and a sub-account. Sub-account is a blob. This blob has to be 32 bytes long. And so when you're writing code to do a sub-account, you need to make sure that you check that it's 32 bytes long. Another caveat that's interesting is that the null sub-account is equal to the 32 byte long all zeros binary string. So if you're writing an equivalence function, you want to make sure that you check that null is equal to all zeros in that account. Then we have a set of methods. So our tokens have names. You'll notice that these are queries. We can assign a name to our token, a symbol. Decimals is a number of zeros. So your balance is a natural number, which means there's no decimals. So we have to tell you how many decimals. ICP has 8 decimals. I believe that Ethereum has 18 decimals. Usually your ledger has a fee and people want to query that so they know how much to send in the fee field. And then you have metadata. So this is important. When you look here, you see that your metadata is a vector of text and value. Now this is not the same value that we'll see later in ICRC3. ICRC3 has a couple more values here, including map. The value in ICRC3 is a superset of this value. And then there's another ICRC called ICRC16, which adds some additional convenience types. And the idea here is that we want to be able to mirror the candid values. Candid is the format of values on the internet computer when they are sent back and forth to different canisters. And so this is an extensible format, this value format, and it allows us to put interesting information in our metadata. Later we'll see we'll define what that is. Total supply, this is a total number of tokens. Minting account is interesting. This is just sort of a standard that emerged because it's the way that the ICP canister did it. If a transaction comes from a minting account, it's considered a mint. And if you send tokens to a minting account, it's considered a burn. So the tokens go away when you burn them. Balance of is a method that takes an account and then gives you back a balance, a natural number balance. Now transfer, this is the one that everybody wants to know. How do I send money? So we have transfer args. We assume that when you call ICRC1 transfer, you're calling from your public key. So we only require the from sub account. If you want the money to come out of one of your sub accounts, you can put the sub account there, set it to null otherwise. Where do you want the money to go to? How much is your amount? Your fee, if you leave it empty, then it's up to the canister to assign a fee. Memo is a blob that you can put there or not. And usually you get about 32 bytes, but it's not specified in the standard that it has to be 32 bytes. If you put a memo in there and you want to make sure that every transaction is unique in some way and doesn't hit what we will see later is called transaction deduplication, then you want to give your item a different memo every time that you send a transaction. Now, if you want it to match, it will hit deduplication if the memos match and they're within like 24 hours if the other amounts match. Then there's a created at time. This is just a protective thing to put in a timestamp. You don't want to create a transaction and sign it, and then for some reason it doesn't make it all the way through to the internet computer, and so you do a new one and you send it, and then later the boundary node finds that and then relays it. If you don't have a created at time on there, you could have more money being spent than you want. You call it with the transfer args, you can get back a number of errors. So the caller pays the fee. You can read some more information about these things here. ICRC1 supported standards is something that like a wallet can call that will say, hey, what other standards do you support? For instance, if you also include ICRC2, which is a transfer from approve workflow, you would want to return those with a name and text. So here we see that we should at least return ICRC1 and point to this URL. Now, ICRC1 is actually being superseded by ICRC10, which is a more generic one. We didn't want every standard to have to implement their own supported standard. So for example, for NFTs, we have ICRC7. We didn't want to have ICRC7 supported standards. So we now have a generic ICRC10 supported standard, and that's all that's in that ICRC. And typically in a token, you're just returning ICRC10 supported standard is the same as what you return for ICRC1 supported standard. Now, extensions, all this is saying is that we can extend ICRC1. If we want to add additional features, we do that through an additional ICRC, and then we will include whatever the extension is in the return of that supported standards call. Now, what metadata is in ICRC1? We have a symbol that is usually a text. We have name, which is a text. Decimals. So all those individual calls, you can also get all that data all at once by calling metadata. Our fee, and then a logo. Typically your logo is like this string. You could also point to a URL if you wanted to, but actually putting your data in the canister is nice because if your source URL goes away, your logo is still available. And now we talk about transaction deduplication. So this basically says that there's this transaction window and permitted drift where we're going to look within the transaction window for duplicate transactions. And if we see a duplicate, we're going to reject it. You can deduplicate by providing different created at times or different memos. And the permitted drift is like too old or too or created in the future. That lets you drift a little bit. If your system clock is off from the boundary node, or the replica's clock, it'll still let your transaction get through. And it talks about the algorithm here that you should implement. Here's more about the minting account, and that's it. That's the ICRC1 standard in a nutshell. So using that, we can build any number of tokens that can transfer one-way token transfers from the sender to the receiver. We've done ICDevs token. This is our project that we've been working on. And you'll notice if we look in our mops.2ml file, we specify that we're dependent on ICRC1-mo 0015. And if we go to mops.1, ICRC1-mo, we should see here, this was uploaded 15 days ago. And it's this repository. Currently in alpha release, it hasn't been audited. If you'd like to volunteer to audit it, we would love to have you audit that piece of code so that other people can start using this in production code. This is the library, version 15. I'm going to go through this code and show you what we're doing. First of all, let's look at dependencies. We're using base 11. We use the AV8 Labs array, stable tree map, stable buffer, map 9, itertools, vector. These are included in mops. For whatever reason, these are not in mops. I think map is in mops now. And then we have some test dependencies, and we can see the definition of our mops file. So as we start to look through our library, we'll quickly see that there are some tools here that we use that are in our project: account, migrations, and migration types. I'll touch on migration types and migrations very quickly, but it probably involves a more robust video. The migration pattern lets you set up your project so that if your data types change as you upgrade, you have a very clear way to transform your old data upon upgrade to the new data types. So for instance, say we decide that the account value needs to now have a sub account. Well, all of our old accounts that are saved in the system, like our balances, would need to be updated to include that new property of sub account. And so we would have to write a migration, and those are pretty simple. You go through here, you create a new folder of your new migration, and you declare your new types in your type file. Here you'll see all the types that we use in this library, and then in your lib there's an upgrade function. And in the upgrade function you get your previous state, and you have to return your new state. So your state looks like this. Here's version 1, here's version 2. And as you add new versions, you would add things here. For most libraries, it's nice to have these debug channels. So if you're debugging, you can turn debug statements off. They take up memory, and if you wrap debug statements in this debug, if you put debug in front of here, when you compile for release, it will remove this, and you'll use a few less cycles. We import a number of our types from our migration pattern, so we can go through and look at the types here in a minute. Then we get to our initial, some functions that are our initial state. This just returns back the default state, what our current state version is. Init, our initialization function, just calls our base migrate function in our migration. And then we pull in some libraries and some functions that we're going to need. And so this is called the class plus pattern. We have all this stuff up here that is in our module, and then we eventually declare a class which takes as an input our state, and then a couple other values like the canister that's instantiating the class, as well as some environment variables that we'll talk about later. If we go back and look at our ICDevs token, we'll see that in our main token function here, we instantiate our ICRC1 state as a stable variable. So this is what our state's going to be. So because it's stable, it will survive upgrades. Our migration pattern should take care of this. We're going to pull our current version out into our ICRC1 state current. Because we do this migration pattern and pass in this initial state, this is stable. So as we upgrade it, it's going to put it into whatever our current state is. So that's a nice pattern. So we don't have to write a bunch of pre-upgrade and post-upgrade code. It just gets taken care of for us in the execution of the class. Whatever we pass in for stored, it will reconstitute the initial state here. And what happens here is if it gets passed in as null, then we get our initial state. And if we pass in a value, it will, remember this is up the migration pattern. So we're passing in whatever stored is, and this will actually upgrade it to whatever our current state version is using the migration pattern. We also have a set of listeners here, and there's a function to register these later, but it allows us to associate a key with a listener, and a listener is just a function. So whenever tokens are transferred with this class, you can register another function to be updated. So if you want to do something fun like mint an NFT whenever somebody transfers some tokens, you can write your own function at the top level actor and then register that function with the class. So you don't have to change anything inside the class. So if you're like, I don't want to get into this, I want to do this complicated thing, but I don't want to have to get into the nuts and bolts of ICRC1, you shouldn't have to. You should just be able to register a new token transferred listener, and then it will be called whenever tokens are transferred. And we'll look at there's an example of that in this, or in our ICRC Fungible project actually, and we'll take a look at that. We can get our state. So if we actually need to do something deep or funky with the state, we do have access to that. That can be dangerous. Know what you're doing when you access state. If you want, this is a get local transactions. So this library will keep all your transactions locally inside of its state unless you override it with a different add records function. So you'll notice in our library that we override that with ICRC3.addRecords, and that hands off adding records to ICRC3 so they get stored in a block structure and get archived and all the great things that come with ICRC3. But if you just want to play around, you do get local storage of tokens. This will return our environment, whatever was passed in. We should look at our types. So what's in our environment? Well, we have a getTime function. We have a getTime function in case we want to use, usually you just pass time.now to this, but if you're doing testing, you might want to test, might want to have more control over your time. Get_fee is a function. This can be null and it'll just use your default fee. If you want to do something more fancy, like we were talking about with like a proportional fee, you can use this get_fee here, and whenever our class wants to ask what the fee is, it'll ask this function. And it'll pass in the transfer args. So if you pass in transfer args with a value of 10 and you want your fee to be 10%, then it will return a fee of 1. And then add ledger transaction. This is where we can overload with ICRC3, and instead of using that local store, it will use ICRC3 as basically the database for our tokens. We can return our text. So you'll notice there's a lot of public functions here that return the things that you would expect from our ICRC1. So here's where we return the metadata. This is a register metadata function, or it lets us add new values to the metadata or overwrite them. Init metadata, you need to call init metadata as part of like your initialization function for your token. If you go back and look, I called like this init metadata function. You can't really write things in your instantiation because some of them are calculated. They need to be done in an init function. So what this does is it goes through and it adds all of those standard metadata items. You can have all kinds of metadata items, but the standard ones for ICRC1, we want to put in there. So for the fee, we get our state fee. For our name, we get our state.name, symbol, logo, etc. Updating our ledger info. This is a function that lets us, instead of manipulating things directly in state, I would advise that you use this function and pass in any one of these variants. If you want to change the name or the symbol or the logo, you would call this function and pass in what you would like to change. There's our total supply. Minted supply returns the number of minted tokens since the beginning. Burn supply returns the number of burn tokens, and so your total supply is minted tokens minus burn tokens. Max supply is an optional value. You don't have to have a max supply, but you can. And if you set a max supply and you try to mint, then we won't mint any more tokens. So we've talked about the minting account, and this will give you the minting account. Balance of. This is probably a great time to stop and go back to our type file and look at our state and how this entire object actually maintains its state. Here we go. So what is our ICRC1 token actually keeping track of? State is everything. The data that you have is your object. You can reconfigure it, you can do new things for it, but you have to have the data that you want to be functional. So we keep track of the number of burn tokens. We keep track of the number of minted tokens. We keep track of this permitted drift and transaction window, which we have kept, which we have mentioned before when we talked about deduplication. Accounts is a type of account, type accounts. This is a map between an account and a balance. So principal and sub-account to a balance. So this is where everybody's stuff is. If you have tokens, this is where it's going to keep it. We have a cleaning timer, which I'll talk about later. Name, symbol, logo, decimals, your fee. Max supply, which can be optional. Max memo. This sets how much data you can put in your memo. You may want to put a lot of information in your memo. Just keep in mind that every byte that someone puts in has to be paid for forever. So if you put a very large memo, people might start writing JPEGs in there, and all of a sudden your ledger is very expensive to maintain. Minting account, your metadata, supported standards. This is the local transaction vector that you can override with ICRC3. Actually, this is actually used for deduplication. Excuse me. So we keep track of the recent transactions. We keep track of the blob, which is a hash of the function, and then we keep track of, I believe, a timestamp. And I'll have to see what the second variable is. It might be the amount. I'm not positive, but deduplication uses this, and the cleaning timer will run every so often, and it will remove things that are within that transaction window out. There is a max accounts that we can have. And when we reach that max accounts, we then have a function that gets called to settle to accounts. So if we set our account max accounts to 100,000 accounts, then we need to settle to accounts of like 90,000. And so what that'll do is if we get to 100,000, it will go and delete the lowest 10,000 accounts. You can have a fee collector in ICRC. It's not really specified in ICRC1, but a lot of the SNS tokens have this fee collector where instead of burning tokens, you can award them to an account. And then fee collector emitted is used to track if the fee collector block, if a new fee collector needs to be added to a transaction, or if we can just write a fee collector block. This is a coming ICRC that'll better handle and solidify how fee collectors are handled. So that's our state. So coming back over here, when we get our balance, we just call get balance of our accounts, and it looks it up in that map. We return back our supported standards. We can register new supported standards. We can add a transaction to our local ledger. Now we have transfer, and this is where all the magic happens. So this is the public function transfer, and it calls this transfer token function and passes everything in. This is what we call the star pattern. When you call an async star, you don't know if this function that you're calling is going to, since we await star, we don't know if this transfer tokens is going to call another canister or not. You may have a canister that says you can only transfer tokens if you are in this list on some other canister. And so when that happens, when the transfer occurs, you need to ask the other canister, hey, Bob, is Bob on your list? And reply back and say, yes, Bob's on my list, and then the transfer can occur. It's possible that if you do that, you may have committed state already. And so you need to know if you need to roll back or not if you use the star pattern. So this will tell you if you can still trap and no state will change, or if you have already awaited something and it's like a warning to say, go back and look because you may need to roll something back. We pass in who's calling it, the transfer args, which we already looked at. System override, we'll see what this does in a minute. And then we have this can transfer. We don't want you to have to edit the library to do cool things. Here, when you call transfer tokens, we want to pass in, by default, if you just call transfer, we're not passing anything in. But if you want to, you can call this function and you can pass in can transfer. Can transfer is a function. It's either a synchronous function or an asynchronous function. And you pass in your transaction, basically the result of your transaction block that's about to occur, this notification object, which also has the details. So you pass this in, what the block's going to be, the details of your transaction notification. What you get back is also what the block's going to be and what the notification is, or an error. In can transfer, you can actually modify or transform the transaction. So say that every time somebody transfers, you want to multiply their amount by 10. I can take the amount, I can multiply the amount by 10, and when it comes back through, we'll say, yes, you can transfer, and this is going to be the amount. When we call can transfer, we may need to run some checks again. So we set up our from variable, and then we figure out if this is a mint, a burn, or a transfer. We then create the transfer request. This is just a utility function that puts it in that notification format. We calculate the fee here, and if it is a transfer, we go and get the fee. We now validate the request. So we're passing in our requirement, and we're passing in our calculated fee, and as well as a system override. We need to look at this validate function and see exactly what's happening. We now create the map, and these maps are used to create a block that's used for hashing. Our pre-notification, we take that request, and we actually have to add the calculated fee to be a true notification. And now we're going to call the handle can transfer. So we had a couple things we got to look at. First, let's look at validate request. So the things that you would expect and the things that are dictated by ICRC1. You can't send to yourself. We check that the account is valid, that it has 32 bytes or null in the account. We check the memo, make sure it's not too big. We make sure that the amount is greater than 0. Then there's some filters that we have to run through based on the kind. So here we want to make sure that we have a fee. We are going to now get the balance. So we go get the balance of our user, and we check that the amount plus final fee is greater than their balance. If they don't have if they don't have that many tokens, they can't send them. Additional issues for minting as well as burning. We now need to deduplicate. So this will check that created it and make sure that if it exists, or if it doesn't exist, we're going to deduplicate our transaction. And that's how we detect duplicate transactions. Then we're done validating. Now we have to handle can transfer. This function will see if there is a can transfer function defined or not. If it's null, then we just return back what we got. If it's synchronous, we're going to call the function, and then we will return back whatever the synchronous function gives us. If it's a remote function, we're going to await it. And then when we get the values back, we'll return it appropriately. Now you'll notice that if we validate here, and then we handle the notification, we get the amount and the 2 out of the notification, we reset up some values that we need to check. And then based off of the kind, we either mint the balance, burn the balance, or transfer the balance. If we transfer, we're going to burn the fee. Then we have to store the transaction. This is handle add record to ledger. If it's overridden, it'll be written to ICRC3. If it's not, it'll be written to the local transaction. We get a final transaction, and then we have to figure out if we have to do anything for the fee collector. We then have to add the representational independent hash of this block to this transaction to our recent transactions. Once all of that's done, we put our balance, and then we handle broadcast to listeners. This handle broadcast to listeners is going to call out to all of our listeners who've registered with us and say, this transfer did occur. Do you want to do anything in response to it? So this is how we will add cool features and reactions to people transferring, minting, or burning tokens. And then we're done. Handling the broadcast is just a simple loop. This handles our fee collector. This handles adding to the ledger, either to our local transactions, or to some overridden value, which would be ICRC3. We can set our fee collector block. We can handle this cleanup where we do the check accounts and cleaning up our recents. Here's a function to mint. The actual minting of tokens. This creates tokens. Burn. Testing our memo. Testing if our transaction is too old. Testing if it's in the future. Finding a duplicate. This is the actual deduplicate function. Cleaning up our recents, checking our accounts. This will let us clean up our accounts if we need to. Validating our fee, getting the fee. Here's some just utility functions that converts a existing transaction request into a value for insertion into an ICRC3. This is what you can call to register the listener. I will note that in transfer tokens, we do check the response. So if you send a notification, and we did that silly example where we multiplied your amount by 10, when it came back, we will double check that the person has that much. So the validate of the request does occur on whatever you transform it to. So that's the security check there. If we look at our canister, this is an example canister, and we'll look at a couple different canisters. But the implementation is now pretty easy. There's a little bit of boilerplate where we define our default arguments, whether or not we pass in any init args or whether or not we're going to use the default args that are inside the class. We have to set up our state. We have to get our current state out of the state. And then we have this little deal here where we have a private ICRC1 that is our class, a nullable class. And you're going to want to call ICRC1 when you use this, because that will check and see if the class has been instantiated or not. And if it has not, it will instantiate it. If it won't, if it's already been instantiated, it returns back the current class. And instantiating the class is what runs the migration to upgrade if there ever are upgrades. Then, once you're past the boilerplate, it's super simple. You need to have each of the ICRC1 functions in your actor, and then you should be able to call, most of these have very direct calls into a simple function. And that's it. We have little deposit cycles here. Now, what can you do with ICRC1 that's interesting? In our ICDevs token, there's some legacy stuff in here that we probably need to delete because it's not relevant anymore, but there are some examples that came from the project that we forked. We'll look at two examples. The first is an allow list. So this one has an allow list. So what does that mean? Well, let's take a quick look. You'll notice that, and this has some ICRC2, 3 to 4 stuff, which we'll ignore for now, but just trust me that the basic ICRC boilerplate's the same for some of those other ICRCs, and we'll get past the boilerplate. You'll notice that when we get to transfer, we pass in this sync can transfer. What does that do? So what we do here is we check an allow list map, or it's a set, and we check if this notification, if the from account is in the set. If it's not, we return an error. If it is, we change the fee to 0, the calculated fee to 0. What this does is, since it's a private token, we don't need a fee. We don't expect these people, we know them. If they start spamming the ledger, we can just remove them from the allow list. So we can set a fee to 0 and we don't have to have a fee on our token. That's how you use can approve. Very simple. Our simple example, we were talking about multiplying the amount by 10. I could multiply the amount by 10 here if I wanted to. So that's really it. Now, if you're not on the list, you can't transfer. So how do you get on the list? Well, we have to have an allow list here that gets updated. We do that. We have an admin function on our actor where we can pass in a bunch of principals that we want either allowed or not allowed, and this will add them to the allow list. So a very simple token. We didn't have to change anything inside of the ICRC1 library. We were able to just use functions in our actor to manipulate the behavior. The other example is a lotto token. So here, again, all of this is the same. We get past the boilerplate. Here you'll notice that we didn't change ICRC1 transfer here at all. It still passes a null for can transfers. This is just kind of a normal token. What we did add was setting up a vector here to track burns. So we're going to have this lotto list, which is an account to a NAT. Then we have a transfer listener that's going to listen for transactions. If it sees a burn, it's going to add the lotto list to the lotto list. It's going to add a burn from and a burn amount. And then it's going to set a timer. Then we have a lotto function. And the lotto function is going to check and see if it has a list, and it will use some randomness. Here we're using non-secure randomness. And what it does is it flips a coin, and if the coin is true, it will mint the number of tokens you burned times 2 and set a memo of lotto, and that mints tokens. So if you burn 1 token, we're going to flip a coin, and if it comes up heads, you get 2 tokens. This is the actual mint function. And you'll notice that we have this register token transferred lotto transfer listener. So we should have this a couple different places. Whenever we upgrade, we need to re-register an item, and then we also have this admin init where we need to call that when we deploy this lotto function, and it will register this. So here we have a listener, and we are notified when a transfer occurs. If it's a burn, we put it on the lotto list, and a timer later will attempt to reward that user who burned if a token flip comes up heads. So again, we didn't make any changes inside the library, and we added cool functionality. I hope this was helpful. I know this video is fairly long and in depth, but if you really want to understand ICRC1 and what's going on, and you want to understand how potentially, I won't say it's easy, but we've tried to make it much easier to build tokens with cool functionality by using this particular ICRC1 library that has the notifications and the event listeners. So check it out. Also go back and check out older videos if you want to see what we're doing with the ICDV token. And I hope to be back soon with next time we'll either do a deep dive into ICRC2 and ICRC3, maybe 4, or we'll get back to building our dApp to help mint ICDV, which you can already do. You don't have to wait for the dApp. If you really want to learn how to develop on the IC, you need to know how to use DFX. And there are DFX instructions in the last video for minting ICDV as well. So thank you all so much for watching. Please subscribe. We're trying to get up to as many subscribers as we can so we can use more and more of the tools here on YouTube to help collect funds that will help the charity do more work. Thanks a lot.